no LED light bulb. This is what we make in our lab. And what is high is a high brightness. You get a lot of lumens. And my student is here. He's involved in making it. And there's high efficacy. The lumens per watt that we get is about 82 lumens per watt. And then it's a high CRI. Well, now what we get is not very high, but this is what everybody's aiming at, the color rendering index I was talking about earlier. And then it's a long lifetime, a really long lifetime. And then what is the aim low that we're looking for is a low weight. The one that I was talking about is a 6 ounce, 170 grams. You put in your hand, it's really heavy. And then here we're talking about less 20 grams. And then it's a low heat. You don't see it, you don't get a lot of heat from this light bulb. And you don't use a lot of materials for it. It's really light. It's less than 20 grams. And the low form factor is really tiny. And also it doesn't use a lot of electricity because of the high efficiency or efficacy that we call. And also it's a very low degradation. A lot of the sources that over time you see the amount of light you're getting is going down. But this is the degradation is almost no degradation, but slowly, very slowly. And then it has no mercury. And the fluorescence light, you know, there's a mercury in there. And then if everybody passed the law, outlawed the incandescent light bulb, changing to all fluorescence. And then when we dispose all this fluorescence light into our landfill, and over the years, our groundwater will be tainted with mercury, because even though for each of them there are tiny little bit of mercury in there, that's all you need to give you the light. But if they are replacing the only light source that everybody's using, is going to be a problem. But for the LED, so it's there's no mercury in there. It's a little tiny semiconductor chip, and there's no organic. This is I just make fun with my colleague, because people are making organic LEDs, and they are very expensive. I said, so we have no organic. So like when you go to the supermarket, when you buy anything organic, it's expensive. So we have no organic, so this is inexpensive. And there's no ballast. Like all the fluorescence light, you need a ballast to turn it on to control it. We don't need a ballast. And there's no time delay, so you turn it on instantly. So with this, all these goodies about the LEDs, so now you can design a little pillbox light, and this is actually a light, a Toshiba light, or a desk lamp. Because of a small form factor, you can put it anywhere you want it. So it can give you a slimline or streamline lighting design. So I know we have some designer here. I bet that they are designing with a lot more freedom with the LED as a light source. So now this is what we call, like I work in semiconductors. For those of you, if you heard about the Moore's law about the semiconductor chips. So this is how like the cost goes down over the years. And then with the speed of the LED or the transistor, that will go up over the years. So what this is the equivalent for the LED, how the cost of the LED goes down over the years from the 1970s, and then how is the amount of light that you get from the LED, how it goes up in the years. And then how the shape of the LED change and the color of the LED change. So at the beginning, you only get the red one, just like those you see in the bus, in the elevators. And then later on, we have the yellow ones, and then the blue ones that came in the early 1990s. And this is actually the major breakthrough when we start having the blue one, because now you have all the colors, the blue one, green one, and the red one. So when you mix the colors, particularly with the blue one, that you can get white. The white color is what gives you the source that we can use to replace the lamp. And then this is, and with the amount of light that we can get from the LED, all different, the technology has been improving extremely fast. And that's why that we are going to have all the light replaced by LED in a few years. So what do we do? In our lab, this PTC, this is our logo. It's Photonic Technology Center. So I just talk about the few of the projects that we do. And one of the, I call it this LED on silicon. So it's something you can pronounce. It's a Lados, and then translated to Chinese. It's a 领导技术. So this is something has a little touch to it. And what we do here, we try to make the LED more cost-effective in manufacturing, combined with the silicon technology. And we're making micro display with it. And then I have a couple demo here that you can look at. And I'm also working with some of my colleagues who work on communications. Like Professor Ben Latave mentioned the Wi-Fi that everybody are using now. So we are working on the light fire. So it's a light fidelity. So the Wi-Fi came from hi-fi. So and then now we have this Li-Fi. So it's essentially we use the LED, the visible light, as the communication tool instead of using the electromagnetic waves. So this can be done also. So one of the grand challenges that we do in our lab is trying to put the LED on silicon. So I'm not going to go into detail of this. This is a lot of material science in it. So we have projects that's supported by RGC and also ITF. I've been getting very, very good support from this government agencies since I moved to Hong Kong. And that's why we can make a lot of these new inventions and a big leap forward with this support from HKUST and also the RGC and ITF. So one of the things that we're trying to do is that we're trying to grow this LED on the silicon. As you know, silicon is a substrate that you make all your IC on, and they are dirt cheap. And then the technology is also improving very fast, and the costs keep coming down, just like the Moore's law I was talking about. So this is one of the things that we are doing. So I'm not going to details in here. And other things that we're trying to do is trying to make the display with it. So now you see, when you go to all these stores, they said you're selling LED TV. They're not LED. That you are seeing it's a display. It's a LCD, liquid crystal display. It's only the LED is the backlight, because the LCD does not give any light. So need a backlight. So what they call LED TV is actually a LED backlight, LCD television. But what we have here is a small one. It's not a TV, but it's a wheel LED. It's a self-emitting. And then these, the LED display that you are seeing, like in Times Square or many of the places, including the NASDAQ billboard. And these are wheel LEDs that you're seeing. So you can watch a movie in the bright daylight. And this is because of the LED. But now each of these LED is individually packaged LED. So this is, I call it, it's like compared with the transistors. That is the transistor in the 1950s. And what we are trying to do is try to integrate and try to make LED like integrated circuits, like the ICs. And then this is the optical communications that people have been doing with the fiber, with the laser light. So I was talking about this light fire. They use the LED to do optical communication, but you don't need a fiber. It's in free space. And you can also call it fiberless light communication, optical communication. So this is some of the current display technology, including this projector here. It's, you use a 3 LCD, or this one here is actually a digital light processor that you are seeing. It uses millions of tiny mirrors that is directing the light. It has a big light bulb and then the color wheel, and this is what you're seeing as a projector. And then these has a lot of problems, like the optical loss with the optical components is over 90%. And then this is a very expensive with the laser and also the rainbow effect. I'm not going to do the technical detail of this. And then there are the newer display technology. There's LCOS, that is a liquid crystal on silicon, and the scanning mirrors. And these are the people are using it to either make the projection or the pico projector, is most of them are used the LCOS, or using this scanning mirror lasers. It's a similar technology like the previous one. Again, because of the optical components, you got to go through the color filters or go through the polarization plates, and then you will lose 60% of the light. So what we're trying to do here is use the LED that you can see directly, and then we integrate it with the AM substrate. It's an active matrix, and this is made with the silicon IC. So when you combine this, we created this lattice chip, and then you can have this micro display technology that we developed in our lab, and also this demo that you'll be seeing. So the idea is relatively simple. We have the LED array, and then after we make the LED, we flip it on the silicon chip. And then this is the LED array that you see here. And this is the technical detail, and you're probably not interested how we make it. And it's similar to people are making the LEDs, but then we leave individual pixel on the same chip. Then when you make it, so after you make it, and then we have this array of the LEDs. And the size of the array, you can change it to any size that you want. And then we have this silicon IC that we make the active matrix. It's 2 transistors, 1 capacitor, essentially. And this is a 30 by 30 lattice chips. That means it has 900 pixels. And then this one is 60 by 60 lattice chip. It has 3,600 pixels. And then these are the size that between the pixels. So this is what the different generations. The first generation, we just make the 8 by 8 array, and then we try to put the color conversion material on it, so to make it full color. And then this is a 60 and 60 array, and then this is one that we have the UST logo. And then there's a HKUST that you can, and then this one we try to project it onto a wall, so you can, because we don't have the optical loss. So after the projection, that you will still see like 90% of the light. And then this is our future work that we try to integrate it with the other silicon components, including the power. So we try to put the passive power on the silicon chip that make the LED have an increase in functionality and also make it even smaller. So this is our future work. So we can also make the intelligent light bulb. So I call it the I light. The I stands for intelligent. So the Apple products, I this, I that. The I doesn't mean anything. And then this is our I light. It actually means intelligent. So we try to make the light bulb intelligent and small. And then it's also the form factor is small, and also you get a lot of use out of it other than lighting. So this is the micro display that I already talked about. And also the light bulb is a light source and also intelligent. And you can like put intelligence into it. Like for example, if there's a lot of sunlight today, it's very bright, and then the light over there, it will have the sensor that it can turn down the amount of light, because all these electronic products, we can integrate them. And then back here, you don't have a lot of sunlight, and then it would turn up, so the whole room will have the same amount of light. And then this is the one that I was talking about earlier. We can use a visible light for communication. And then a lot of people ask, what's wrong with Wi-Fi? There's nothing wrong with Wi-Fi, but then you need to install the Wi-Fi. Now we have the light there. It's already installed. It's already there. So why don't we just use it to do something else? Like in the supermarket, then if the light's already there, then we can use this light to beam the information to the shopping cart. So when you get by, it can tell you, hey, this is on sale. And then this product is have a certain information that you can find. And then in the car, the traffic light can also beam information and communicate with the cars, the oncoming traffic. And you can like sense this, hey, there's a lot of pollution out there. And then you can tell there's the people that drive by. So this is what we're going to use as a light fire for. So this is a comparison of the display technology of our lateral display compared with the LCOS. All of them, they are based on, will need a very high power backlight. So the LCOS will have this backlight here. This also this digital light processor is also need a backlight, and then the LCD also need a backlight. So our advantage is you can see it directly, and it doesn't need a backlight. And also, you must all have the experience that when you have a digital camera, when you take out, you want to take a picture under the sunlight, and then you look at it like this. Another one of our students says, you want to shade it, otherwise you don't see what's the picture you're trying to take in the little display. So with the LED, you won't have the problem, just like you can see movies in the sunlight in Times Square during the daytime, because you see the light emitting directly. And then also for the heads-up display in the car, so you can put it up there and then get all the information on map and whatnot. So this is a little display that we have that it can show you HKUST and also maybe our logo later. And then this is another one of our concepts that's think of the bulk concept. I mean, for the traffic lights, it's always 3 colors. But why do you always need 3 colors? So we said, why don't you just have a single traffic light there? And then the source will be our intelligent lattice chip. And then all you need is a little projection lens, because you don't need to project very big, about this size, 8 inch. That's all you need. And then we can just cycle through it. Okay, when there's a walking, we show this. And there's yellow light, how many seconds is changing, and then stop is like this. This is for the pedestrian, and these are for the cars. So it will save you 1/3 of the material. And then using the LED, a single chip would do it. And then you can program it and just do this simple test. It's very simple. And then here, if you have this traffic light in the heavy traffic area in Causeway Bay or Mont Carp, and then we can also integrate it with a sensor, and then it can sense this pollution, what's the API today, and then we can display it, and or somebody can come by and take the data,